Half of your colleagues will miss the start. So this is lecture 3, and in this lecture we will be discussing diodes mostly. This is the first lecture, which is new material. That's what we did last lecture, which you should probably read yourselves. So this time it's some terminology, that's to say the difference between active and passive components. And then we'll talk about diodes for a bit, in forward bias and reverse bias. Have you done the LED thing yet? No. Oh, that's good. To come then. That's lucky for you, you've got it the wrong way around. Lecture first, then laboratory. So you'll know what you're doing of when you get there, in principle. Obviously we like it the other way around because then it makes you figure things out, but it can't always work that way. So we'll talk a bit about when a diode is conducting and when it's not conducting, and when it's neither one or the other. And we'll think about it as only possessing one of those states. So it'll be either off or on the point of turning on. And I'll spend most of this lecture doing a quite comprehensive example of how you solve problems of circuits with diodes in, and whether the diode is conducting or, and what's going to happen in the circuit due to the existence of the diode. But first we need to just define a few terms. And we'll say that a signal is a voltage or current or other measurable quantity. So it could be power, could be torque, speed, carriers per second crossing a potential barrier, anything you like. Although it's tricky to measure that one. Which carries useful information. So if you had an audio amplifier or some such, you'd have to give it some DC power supplies to make it go, which would be derived from plugging it in the wall, most likely. And then you'd have to plug your MP3 player in the front, or CD player, or I don't know, record player. Record players are great. Basically, a piece of crystal on the end of a scaffolding pole, all suspended on an enormous arm, which just wibbles back and forth. It's so simple and beautiful and elegant, but not nearly as good as a CD. Anyway, some sort of information has to be in this signal. It can't just be DC. Although on or off is information, as long as it's meaningful. But if it's just on until you're finished with it, that isn't a signal. It's bias. So it's a constant voltage or current which is used to set up favourable quiescent conditions. Quiescent conditions means without signal. So when there are no signals around, you haven't pressed play yet, there may be some voltages or currents that are flowing through the circuit or measurable on the circuit, which are there in order to make active components operate in the region that we expect. And we will see in a minute when we look at the diode that there are different methods or different modes of operation. And this is what makes active components not like passive components. If you've got a resistor, which is passive, it requires no energy other than the signal. So if you had it on the desk, you'd know what it was going to do. If you applied anything to it, it would give you V as IR, assuming you didn't heat it up too much. Whereas a diode on the desk with signal applied will not behave the same as a diode on the desk with bias applied and then signal applied. Depends on how much bias. And that's an active component, is you must apply some other voltages or currents to it to make it do what you want. And this will become clear throughout the course of this lecture, I hope. So a diode is a two-terminal electronic device that allows current flow in one direction only. So it's like a door with a spring. You can go through it one way, assuming you can't pull the door. No opposable thumbs allowed. You can push the door and it will close itself, and from the other direction you cannot go through it. Diodes are non-linear circuit elements. That's to say you can't have the same response in terms of voltage and current through all parts of its operation. literally you can go through the door one way, but you can't come back. With a resistor, doesn't matter which way the voltage is applied, you'll always get VSIR. And diodes are active components, no surprise there. And we can produce them by several technologies, including thermionic valves, semiconductor metal junctions, which you'll see in the LED thing. Well, it won't be a secret because you've got the pack. You get a little bit of indium phosphide or something, and you drop some indium on top, and then you heat it up to make the indium sort of relax into the anneal actually into the semiconductor, and it forms a close metallurgical contact, and then you pass current and light comes out. So semiconductor metal junction or semiconductor junction. And as far as normal diodes that you just use in circuits, it's almost always semiconductor. So on the left is a, I don't know, 1M4000 and something or other. And that's a regular diode you put in a... It didn't last long. You're all very brave, if that's the average time. Yeah, so the one on the left is sort of regular rectifier diode that you put in, I don't know, if you're making a guitar amp and you need to build a power supply for it first, the diode's going to look like that, and you have 4 of them in a fridge, and we discussed that before Christmas. The one on the right is the sort of thing you might put in a really big drive for a machine, maybe 100 kilowatts or so. You could have 6 of those in some sort of 3-phase bridge arrangement, and that will, the top, as we look at the top side, is where you bolt the heatsink, and that's going to be about that big, so it's about the size of a hockey puck. So as I've already said, by far the most common is the silicon PN junction diode. Both of those pictures are going to be silicon PN junction, and that's formed by 2 pieces of semiconductor, which hopefully this is not news. I take it you've got this far with Prof Houston. Good. So you're all sitting there going, oh no. It's formed by 2 pieces of semiconductor, one doped N-type and one doped P-type, which is the question of how many free electrons and how many free holes. In close metallurgical contact, that's spelled metallurgical wrong. Whoops. And the N-type material is doped with impurities to add electrons, and the P-type is doped with impurities to add holes. And an alloy of metals are deposited, I should say is deposited, because it's one alloy. There's one alloy of many metals, so it should be is deposited on the surface of both. So on where the wire meets the P and where the wire meets the N. And this allows us to make ohmic contacts between the semiconductors. The question of whether a semiconductor metal junction is ohmic or rectifying will probably come up in the other half of 118 if it hasn't already. And the picture on the right is not my finger, so if you watch the video that picture will be blurred because I don't own the copyright to it. That is a power module which contains half a dozen transistors in some sort of bridge configuration. It's blown up, and all the fine little wires are bond wires between the semiconductor and the package. The big pink thing is somebody's finger. So diodes can be forward biased or reverse biased, and under forward bias they have the Shockley equation, which is also familiar. How far have you got, just so I know, in the semiconductor bit? Where are you at? No one knows where you're at. What's the last thing that was said? Other than next week, James will be here. Just before that, what was said? Oh, come on, someone must know. One of you must have been there. What's the very last thing that was done in 118, part 1? Derive the diode, right, so you're on the brink of finishing diodes, more or less. Or you're somewhere in it. Right then, so diode equation isn't news, but it's quite new. So I is the total current, I0 is the saturation current, which we'll talk about in a minute. V is the anode to cathode voltage, where the anode voltage is more positive. Q is the electron charge, K is Boltzmann's constant, and T is the temperature in Kelvin. So room temperature is 293.15 or so, which is 20 C. And we can see on the left the symbol for a diode, and the bar is the cathode. And under forward bias, that will have the lower voltage. And the non-bar, just below where the current symbol is the anode. And there is no positive and negative. And if you say positive and negative, no more biscuits. That simple. It's anode and cathode. And the reason is, you can't say positive and negative just because you can turn them round. You could be really rebellious and put the diode in backwards just to see what happens, in which case the cathode will be positive. And something will happen. Depends what diode and how much voltage. But never plus and minus, only anode and cathode. Always and forever. So forward bias characteristics, that's anode more positive than cathode, is shown for a silicon diode on the right. And we usually say turn on about 0.7. Now, on that particular graph, between 0.8 and 1 looks quite linear. Actually, it is exponential, and if I'd gone a bit further, you'd see it starts to turn quickly. But the fact that it looks nearly linear will come back to help us later. Strictly speaking, though, it is exponential, and that graph does follow the expression in the slide. It just is linearizable over a small region. So when a positive voltage V1 is applied to the P region, anode, with respect to the N region, cathode, the device is forward biased. You can work out which is anode and which is cathode, and or rather, knowing which is anode and cathode, you can work out which is P and N by figuring out where the majority and minority carrier flow is. But that's a semiconductor problem, I'm not doing it. Because you will have to do it elsewhere. So a certain value of applied bias is necessary before an observable current flows. That's to say, between 0 and 0.6 something or other, nothing happens, more or less. But after that, a very small change in voltage will lead to a proportionally much larger change in current, and the relationship is exponential. And for a silicon diode, it's 0.7 volts. For other material systems, it's other voltages, and generally speaking, bigger band gap, bigger turn-on voltage. So we'll call this 0.7 volts the forward voltage drop, and we'll assume from now on, well, from end of this lecture on, that it's 0.7 volts forever, and that we will only talk about silicon diodes. So what we'd really like is a model for a diode. And the reason we'd like a model is if you start solving circuits with the diode equation in, the maths gets really nasty quite quickly. Even for a very simple circuit, it's a bit of a pain. And what we'd really like to be able to do is solve circuits on the back of an envelope without having to think too much or resort to using a PC, because we won't always have one. So we can have a model of a diode which just says it's a door with a spring. This is the electrical equivalent of the door with the spring. You can go through it easily by going right from 0, and you cannot pass through it if you go left from 0. No current will flow, however much voltage I apply in this direction, and the current that flows if I go to the right is limited only by the things that surround the diode. So if you had a diode, and if you had a voltage source and this diode, and you put 0.001 volts on, however much current that voltage source can supply is what will flow. And if that's infinite, that's what will happen. Obviously it won't happen, really, but we don't really have this diode. It's just a model. It's only a model. So this is the simplest model that you can possibly use. And something that's quite interesting about it is it's incapable of dissipating any power. This caused an awful lot of trouble last year, but if there's no voltage across it, doesn't matter how much current there is through it, IV is still 0. So this is a really ropey model of a diode. It's the very worst case, and we won't use it again at all. The only reason you see it now is because it introduces what comes next. But the key thing to remember is this is the electrical equivalent of a door with a closing spring. We can improve it slightly by saying that we're going to add a turn-on voltage. So now we've got the same arrangement but just shifted a bit to the left, right, left, right, up, down, anode, cathode, you can say. So now we've moved our point where the door opens to 0.7. So that's the same as our forward voltage drop, which is handy. And we've got a little circuit. And if we analyse this circuit, we can say, well, let's assume the diode switched off. If it is switched off, then there won't be any current flowing because there's no circuit. And then we can say, well, what will the voltage where the diode used to be? If we just unplugged it, what would the voltage be? Any takers? Biscuits involved. And if I took the diode away, how much current can flow in the circuit? None. Could you follow that up with what will the voltage be across where the diode used to be? Zero. Zero and infinite, blind. 10 volts. Right, there we go. 10. You can have a biscuit for whatever it was you got right. If you want one. Right, now you have to promise to pass them down to 10 without eating too many of them. So it'll be 10 volts across where the diode used to be, because there's no current flowing in the resistor, there is no voltage dropped across it. If there's no voltage dropped across the resistor and one end is connected to 10 volts, the other end must be 10 volts as well. Biscuits have never reached you, did they? Oh, they did? Okay. So then we can say, well, if there's 10 volts across where the diode used to be, and we put the diode back in, it will switch on, because it only needs 0.7 and then it's on. So our initial assumption that says the diode is off was in fact not right. And now we've got to think about what will happen if the diode is on. And we can replace the diode with a voltage source whose value is 0.7. So we'll take the diode out, throw it away, and we'll put in its place a voltage source with value 0.7. So now we've got one voltage source on the left of the resistor, which is 10 volts, and one voltage source on the right, which is 0.7. So what will the voltage across the diode be? I'm sorry, what will the voltage across the resistor be? 9.3. So how much current will flow in it? Carl, you don't need a calculator for that, it's 1 kilo ohm. 9.3 divided by 1 times 10 to the 3. 9.3 milliamps. Written on the next slide for those who are feeling not too studious. Would you care for a biscuit? It's up to me. Oh, right, okay. Good, no then. Pass them down, will you? It's not even written on the next slide, it's written on that slide. It's a giveaway this, isn't it? So we will come back to the analysis of diode circuits in just a few minutes, but first of all, the question is still unanswered as to what happens if you did put the diode in backwards, or you made the cathode a greater voltage than the anode. There are some reverse bias characteristics, and up to a certain voltage, which is predefined and you can read in the data sheet, nothing will happen except the saturation current will flow. Thereafter, the diode will either break, if it's supposed to be a forward bias operated diode, or it will go into reverse breakdown. And if it is designed to operate in reverse breakdown, it will survive, assuming your circuit is sufficiently well designed that it isn't going to die anyway. And the voltage that it will break down is selectable, so you can buy these Zener diodes for about 4.3, 4.7, 5.2 and so on and so forth, all the way up to a couple of thousand volts, and it's selectable. You just order a different part number and a different breakdown voltage will arrive. And this is really handy for making things like references, because the breakdown voltage is proportional to the band gap of the material and the thickness of the diode material that is being broken down. You could make one out of air if you wanted to, and you could get 1,000,000 volts per meter. Obviously, you wouldn't want a full meter. Although, saying that, if you actually had a meter of air, it would have to be at a certain pressure and a certain humidity and so on and so forth to actually get your 1 megavolt. But from the purposes of making something that will break down at a set voltage, that's more or less right. It's the same process as happening in a semiconductor. There is no arc. It's just that carriers will flow when the breakdown field of the material is exceeded. So when we look at diode data sheets, we'll read off either repetitive reverse maximum or peak inverse voltage. Normally it's RRM, and that says you can go this much in reverse bias, nothing bad will happen, over and over and over for the full life of the diode. So actually you can often go a bit beyond that. If you're buying a Zener diode, it will be written in the part number, something like BCX55C4V7 will be 4.7 volts. We will come back to Zener diodes just before Christmas. So when we did that little diode example, I started off with what happens if it's not there, and then we worked out what would happen because it wasn't there. And once we decided that it would be switched on, we put it back in and did another calculation. And embedded in that is the three sort of states that we'll worry about. And the first one is that the diode is in conduction. And a diode is conducting if the magnitude of the current flowing in the diode is greater than 0. It doesn't say anything about the voltage that's across the diode. And a diode ceases to be in conduction when the current falls to 0. A diode is on the point of conduction if the anode to cathode voltage is 0.7 volts and there is no current flowing. So if your circuit gets the diode to 0.7 volts anode to cathode with the anode more positive, but because of the way the circuit is configured, no current is flowing, then the diode is on the point of conduction. And a favourite question is, determine if this diode is conducting, and then you'll do some calculations to get an answer. How much would I have to change resistor number 1 by to make it on the point of conduction? So oftentimes you work backwards to that point. And a diode is switched off, or rather, the diode is switched off when there's no current in it. The beginning of conduction is when anode to cathode voltage is more than 0.7 volts. So 0.71 is enough. 0.701 is enough. Any more than 0.7. And we'll have a general method for deciding what state and whether it's conducting or not. I've given you a little flow chart. So we start off assuming the diode is not conducting. And then we replace it with an open circuit. If you're finding it a bit small in the handout, you can download the slides off Hercules and have it in Technicolor and everything. So having replaced the diode with an open circuit, we'll work out the voltage across it. So where it used to be, we'll work out the anode to cathode voltage. And if it's more than 0.7, the assumption is... if it's less than 0.7, you might want to change that. No, that's right. It is right in the slide, my bad. Yeah, if the diode anode to cathode voltage is not more than 0.7, the assumption is correct, the diode is switched off, and you can move on to the next diode until you've done them all in the circuit. And if there's more than one diode in the circuit, and you do the first one and it's turned off, and you do the second one and it's turned on, and when you did the first one, you assumed they were all off, you've got to go back and do the first one again, now having the new knowledge that the second one was on. There's only one or two questions in the problem sheets where there's two diodes. That's terrible, isn't it? If it is more than 0.7 volts, then the diode is conducting. And you replace the diode with 0.7 volts, which is what we just did, and we work out the current through the diode, which we just did. So, for the simple conduction state example, we ran through this earlier. So, top circuit diagram is the actual circuit. Middle circuit diagram is we take the diode away, work out the voltage VD1, which is the voltage across the anode and cathode, decide that it's 10, and realise that's more than 0.7, replace the diode with a 0.7 voltage source, 0.7 volt voltage source, and work out what voltage is left to that resistor, and it's 10 minus 0.7, which is 9.3, and then we work out the current with Ohm's law. Let's do a realistic one, or a more realistic one. In the circuit below, determine if the diode D1 is conducting. If D1 is conducting, find the current ID1 flowing through it. If D1 is not conducting, find the magnitude of the reverse bias voltage across it. And you can do it by loops, or you can do it by nodal analysis. So you first of all take away the diode, then you draw on your nodes, or loops, then you do your analysis, then you get the voltage across the anode cathode. You've realised that it's pretty obvious that this is going to be a conducting one, because I wouldn't stop an example halfway through. So you'd realise the diode is conducting. Then you draw the circuit again with the 0.7 volt source instead. Then you draw out some new loops. Then you do your loop analysis again, or the nodal analysis, or whatever. And then you get the current in the diode. As it is, I don't want to do that. I'd rather do it by superposition. But it's up to you how you solve it. All analysis that's valid for circuit theory will work with this, with diodes in the circuit, because what we're actually doing is removing the diode and putting in some things that are linear. Because the source is either off or it's on. And when it's on, it's got one value, and when it's off, it's got another value. That makes it linear. It's linear in two different bits. There's a linear bit where it's off, and a linear bit where it's on. But there is no e raised to the whatever. Although if you use a computer circuit simulator, it's doing the same thing, but it's just doing the horrible maths for you. So we'll use superposition. And the first thing we need to do is to remove the diode. So I've taken the diode away, and now I need to know what's going to happen with the anode to cathode voltage. And I've drawn the arrow in the way where the anode is more positive. So if this answer if VD, as I've drawn it on the diagram, turns out to be negative, diode will probably be off. Or the diode will be off, I think. I got that right. Yes, because you'd have anode to cathode of negative, it was negative, so the diode would be off. So I'm hoping for a positive voltage, VD. The next thing I'll do is I'll take away the 30 volt source. So diode's gone, 30 volt source is gone, and for the 30 volt source, because it's a voltage source, we'll replace it with its internal impedance, as per last lecture, which is 0, because it's a perfect source. There is no internal impedance. If we wanted to, we could try and work out what would happen if we put R3 inside the Thevenin source as well, but I don't want to do that. It complicates matters a lot. The trick with this is to learn the method. This example will not come up on the exam. Definitely not. It's working out how to, clearing up in your head how to do any possible question using this method. There is no point in learning the numbers, they will change, and so will the shape of the circuit. So the 30 volt source is gone, and we've replaced it with a short circuit. Now all that's left is for us to worry about where the 2 amps goes. Now we could redraw this diagram so that R2 and R1 are together and they're 110 ohms. Is that unclear at all? In series, so you add them, as per lecture 1. And that brings us down to 2 parallel branches of differing resistance. So we could say, well, the current will be shared out in proportion to the size, the magnitude of the resistances, and the lower the resistance, the more current you get. And you'd share it out in the same way that you share apples between friends in GCSE maths. But to write it out in equations, we'll say that looking at IR2, it must be minus I, because the direction of I1, I was correcting these last night, I missed that. Right, in equation 1, minus I should read minus I sub 1, because then it matches the diagram. You can change it now if you want. Looking at the way I've drawn IR2 on the diagram, I1 must be going the opposite way, because there's only 3 resistors, and we can see just by looking at it, by inspection if you like, that I1 will be flowing in the opposite direction through R2 as IR2 is drawn. So that's where the minus sign comes from. And then we've got R3 over R1 plus R2 plus R3 will give us the current in R2. And we just run it through. R1 is 100 ohms, R2 is 10 ohms, R3 is 10 ohms, and we'll end up with minus 166.66 milliamps. And if we want to know what VR2 is, which I've also labelled VD, but it's the same, because we've got the voltage across R2, it is IR2 times R2, and that's 10 ohms, so minus 1.66 volts. That's reasonably routine. Next bit. So we'll take away the current source, having obtained the value of voltage across the diode as a result of its existence, and we'll have to replace it with an open circuit because its current source and its internal impedance will be infinite. So that's open circuit. The other thing I've done is I've cheated and turned the 30 volts round. If you look at the original diagram, it says positive on the voltage source is, or the more positive value of the terminal of the voltage source is at the top, and I've written minus 30. In this slide, I've turned the voltage source round and got rid of the minus sign. That's perfectly legal as well. So now I've got to decide what's going to happen here, and this is also a reasonably easy circuit. The point of the superposition method is that you don't have to worry about writing out too many equations for loops and nodes and all that. If you reduce it to the point where it's just a couple of resistors and a single source, you can often use Ohm's law and well, the brain power. There's no method other than you look at it and decide which currents you want to select for and use Ohm's law to find out what's going on. So IR2 now, they're all in series. You can redraw that, so R1, R2 and R3 are in series, so you can work out the total current because it will be the total voltage divided by the total resistance. Happy with that? And it will yield a quarter of an amp. And then we'll multiply through the current by R2 to get the value of the voltage across it, and we'll get 2.5 volts. Now we know enough to work out what's going to happen. Because once we've gone through every source, we'll be able to add all the voltages due to each source across the diode up. And when I say add them, I mean if one was negative, it will be subtracted. but we will do first voltage plus brackets, maybe a minus sign, second voltage plus brackets, and so on and so forth. And it's 2.5 minus 1.66666, which is 0.83, which is more than 0.7. So now we will go back and work through the same thing, but knowing the diode is switched on. So we will firstly consider the current source. And the voltage source, which the diode is now represented by, is switched off. So there is a 0.7 volt voltage source where ID is, except I've switched it off because I'm only considering the 2 amp source. So in this situation, we cannot say the diode is switched off because we've taken the diode out and got rid of it, and we've put in place 0.7 volts voltage source. And now we're doing superposition, and we've decided not to start with that source, so we've replaced it by its internal resistance, which is 0. And that's how we've arrived at the short circuit. Everybody all right with that? Sure? Maybe. So we'll do the working out again, and it will be ID is still flowing the wrong way compared to I1. Oh, I'll put the I1 in this side, that's good. And it will be R3 upon it's 11 right. Why missed a resistor out? Can somebody do on a calculator equation 12? See what the answer is. It's alright, R2 shorted out. No, it's alright. I was expecting to see R2 in there, but it's shorted, so it's fine. Good? Yes. You have complete faith in me to mark your exams, right? So R2 is shorted, so we just don't have to worry about it. And we'll have the current I1 is shared out between R1 and R3. So it's just a current sharing circuit, and the bigger resistance gets the smaller current, so ID1 will get 10 upon 100 plus 100, which is 10 over 110 times 2. Switching off the current source and turning on the 30 volt voltage source, we have still got R2 shorted out because the voltage source that represents the diode is still switched off. So we have V1 upon R1 plus R3 because R3 and R1 are in series and R2 has nothing to do with it because the current will preferentially flow through the short and not through the resistor. So 30 upon 110, which is 0.27 recurring. Happy with that? As happy as is possible under the circumstances. So lastly, we'll worry about the effect of the diode on the circuit. Now, I know this diode is conducting. I know that because when we started all this, the first half of it, we worked out whether it was conducting or not, and it turns out it is. So I know it's conducting, and I know that the current that's flowing in it will flow from the anode to the cathode. And if you look at the very first circuit diagram, you can see which way around the diode is in the circuit. So I know that ID must go upwards on this diagram, even though it's flowing into the source. Now, a while ago, we might have said something like, voltage sources always have their current voltage in the same direction. Or you may have heard it in 117. It's true with the caveat that the source in question is delivering power to the circuit, if you are extracting energy from your source and putting it into your circuit, then the current and voltage will be the same direction. But this is secretly a diode in disguise, and the diode cannot deliver any energy to a circuit. So for this voltage source, I know it will be dissipating power, which is completely fine, nothing wrong with that at all. If you had a 10 volt voltage source and a 5 volt voltage source and you put a 1 ohm resistor between them, you'd get 5 amps flowing from the bigger source into the smaller source. And the smaller source, the 5 volt one, would be taking energy out of the circuit. It would be taking it from the bigger source. Well, similar arrangement here. I know the current must be going into that 0.7 volt source, so I know it's going to be dissipating energy. And that's fine. On the other hand, when I do my circuit analysis, I'm almost certainly going to go, well, voltage and current in the same direction, because that's what we apply. So I've got minus ID everywhere, and it's R2 is in parallel with R1 plus R3. So R1 and R3 are in series, both in parallel with R2, and we'll arrive at VD upon R2 plus VD upon R1 plus R3. And that will yield 0.7 over 100 plus 110. And that's minus 76.36. So for this source, on its own, voltage and current in the same direction. Current flows out of this source and delivers energy to this circuit. But this isn't the whole circuit. This is the circuit minus the 30 volt source, the circuit without, not minus in the mathematical sense, the circuit without the 30 volt source and the 2 amp source. Obviously, a diode in a circuit on its own, with no other power sources around, will be switched off. But this is not really a diode. We've taken the diode away and put 0.7 volts in there instead to model its turn-on voltage. So, last thing to do is to say the contribution to the current flow in the diode is the sum of all of the paths that we had, which is the current in the diode due to the 2 amp source, the current in the diode due to the 30 volt source, and the current in the diode due to the source which represents the diode. And it's, whatever it is, 14.54 milliamps. And the negative signs there are due to the direction of current, and it's all consistent with the diagrams which we've done previously. So if this was a real question, and this one won't be a real question, but this is the style of question that you will find on the problem sheets, which will come your way next week. And it's consistent with the style of question that you will find in the exam and in the midterm. You all got an email about midterm, right? Some early day in February, 4th I think it is. Is it? The staff Christmas dinner might be on the 5th of December. I think your midterm is on the 4th of February. Or maybe your midterm is on the 5th of February and my dinner is on the 4th of December. I have no idea. 4th, is it? Right, good. Better put the dinner in my diary then, hadn't I? If this was a real question, that would be worth about, I don't know, 6 or 7 marks probably. And the way it would work is for every diagram that you made it through, you gain an extra mark and get one for the right answer at the end. So the numerical answer can only gain you a mark. And it can only gain you that mark if I can work out how you got there. You pluck the number out of the blue air, I'm not going to be inclined to believe you. So you must show your working. Draw plenty of diagrams, and don't worry about running out of space. The books are enormous, and even if you do, you can get paper. There is nothing worse, actually. A totally empty book is really good, because they can just flick through and go, nothing. Obviously that's filled with total sadness, because it means I've failed to make you love electronics. But if you've got a stack of about 100 to do, a couple of those does go down quite well. but you won't run out of space, so draw out plenty of diagrams and let me know your logic, because it's the logic that you get the marks for. Almost all the marks are not gained in the answer, they're gained in getting to it. And if this was a real question, the next bit would be, what magnitude would V1 have to be changed to in order that no current would flow in the diode? So on the point of conduction, I'm looking for 0.7 volts across the diode and no current through. So we've got to change the 30 volt source by some voltage that we don't yet know that will yield 0 as an answer in the equation on the slide. 0.7 volts across the diode and no current. And that is what we will worry about for the first half of the next lecture. So today we started off with the terminology, bias signals, passive and active components. Then we had a quick look at diodes and had a look at diode characteristic. And then we briefly considered how a diode is constructed from semiconductor materials. And we considered the effects of forward and reverse biasing a diode. And then I gave you two linear models, one which was just diode conducts when the voltage is anode to cathode is positive, and diode doesn't conduct when the voltage anode to cathode is negative. And after that, I said there are three distinct states of the diode. It's conducting, on the point of conducting, or the other one. I want to say not conducting, but it isn't not conducting. It's the beginning of conduction. Alright, so strictly speaking, two states, and to say that after you've gone through the point of conduction, where there is no current but there is 0.7 volts, after that there will be current flowing and somewhat more than 0.7 volts. And in a real diode it will be exponentially related. And then I started off with this general method of solution for circuits with diodes in, where you decide if the diode is conducting or not. If it is, you replace it with a 0.7 volt voltage source, do your calculation, figure out the current. If there's another diode, you then assume that's not conducting, and carry on in that fashion until you've done all the diodes. And if you find that one's conducting, and previously you assumed that some others found out they were or they weren't, you've got to go back and have another look. So when you come to the problem sheet and there's two diodes in, you could potentially have 4 problems to solve. First one conducting, not conducting. Second one not conducting, conducting. Back to the first one because everything's now changed. Back to the second one to make sure that the first one changing hasn't changed the second one. But it's very unlikely that a 2-diode question would turn up on any test that you might have to face at some point in the future, because that would be very mean. That's not an excuse not to do the questions, though. There he is, my mate.
Yeah.